Welcome back. In Module 1, we talked about the bit, the fundamental unit of classical computing. Think of a classical bit like this coin. It can be heads, which represents a 1, or it can be tails, which represents a 0. At any given moment, your laptop, your phone, and the servers running the internet see the world exactly like this. It is either one state or the other. There is no middle ground. It's binary. But the quantum world, the world of atoms and subatomic particles, doesn't play by these rules. Quantum computers use qubits, and a qubit is capable of something called superposition. To understand superposition, we have to stop looking at the coin lying flat. We have to look at this. Look at the coin now. While it's spinning, is it heads or is it tails? If you said it's both, you're getting close. If you said it's a mixture of both, you're even closer. In physics, this state, where the coin is spinning and hasn't fallen yet, is superposition. A classical bit must be 0 or 1. A qubit, thanks to superposition, exists in a complex linear combination of 0 and 1 simultaneously. Scientists visualize this using something called the Bloch sphere. In a classical computer, you can only be at the North Pole, 0, or the South Pole, 1. But a qubit? A qubit can point anywhere on this sphere. It can be 50% 0 and 50% 1. It can be 70/30ths. The possibilities are infinite. This is where the power comes from. A qubit holds much more information than a simple on-off switch. But here is the catch, the weirdest part of quantum mechanics. As long as the coin is spinning, in superposition, it holds that complex information. But the moment we measure it, the moment we look at it to check the answer, it chooses. We force the universe to make a decision. In physics, this is called the collapse of the wave function. We can't actually see superposition. We can only manipulate it. When we finally ask the computer for an output, the qubit snaps out of superposition and becomes a boring old classical bit again, either a 0 or a 1. So why go through all this trouble if it just becomes a 0 or 1 at the end anyway? Because while the qubits are in superposition, we can perform calculations on all those probabilities at once. A classical computer tries to solve a maze by running down one path at a time. A quantum computer, using superposition, can explore every path in the maze simultaneously. It doesn't just work faster, it works in a fundamentally different way. So, superposition is the ability to be in multiple states at once, like a spinning coin. But one spinning coin isn't enough to build a supercomputer. To do that, we need to make our spinning coins talk to each other. We need a way to link them so that if I touch this coin, that coin over there moves instantly. That is called entanglement, and it's what Einstein called spooky action at a distance. We'll decode that in the next lesson.